Let's talk about critical points and Fermat's theorem. Now, we're going to start by looking at a definition. We're going to let C be an interior point in the domain of F. So an interior point means it's not one of the endpoints. It's on the inside, in between the two endpoints, okay? And we are requiring that this critical value C is inside the domain. So we say that C is going to be a critical point of F. They sometimes call it a critical number of F if the following is true. We need either F prime of C is equal to 0 or F prime of C does not exist. Okay, so I thought we would take a look at a few examples on the right side of this page right here. So when we look at this graph is the graph of some function f of x. And I hope we can see that right here at x equal to 0, we're going to have a horizontal tangent line. So that tangent line is horizontal there. That means that at x equal to 0, we have a critical point or critical value or critical number. At x equal to 1, I have another horizontal tangent line here. So that means that we have a critical point or a critical number at x equal to 1 as well. And then we can see that we have a cusp or a little corner at the value of x equal to 2. So x equal to 2 is also a critical point or critical value or critical number. All right, so in this example, we have 3 critical values. I want to talk to you guys about Fermat's theorem next. So it's not Fermat, it's Fermat. I think he's French. The theorem basically is an if-then statement. So the if part is this whole first line, and then the conclusion, the then part is over here. So what does Fermat's theorem tell us? Well, Fermat's theorem basically says if f has a local maximum or a local minimum at the number c, and if f prime of c exists, then f prime of c will be equal to 0. Okay, so it's basically saying, you know what, whenever you have a maximum or a minimum at this point c, and you happen to know the derivative exists, then that derivative has to be equal to 0. So if we looked at our example up above over here, this function f of x is not differentiable at 2, but this does not violate the theorem because f prime of c doesn't exist on this picture up here. So this is not a counterexample. Fermat's theorem just doesn't apply for this particular point. So I want to look at the converse of Fermat's theorem. Now remember, this is an if-then statement. So if this is true, then this is true. So let's first write down what the converse is going to be. So the converse statement is going to be if f prime of c is equal to 0, then f has a local max or a local min. And this statement is not true. I could give you a counterexample. Let me draw a set of axes here like this. And let me choose a function. Let me graph a function that looks like this. Okay. Anyone guess what this function looks like? If you guessed that this function was f of x equal to x cubed, you would be correct. Notice that when I take the derivative f prime of x, I'm going to get 3x squared. So f prime of 0 is equal to 0, but 0 is not, or f of 0, I guess, is not a max or a min. All right. So this is kind of a counter example to the converse. So to be perfectly clear, the converse is not true. All right. Cool. So let's wrap up this video by talking about the 3 different ways a function can fail to have a derivative at some point c. And we're going to draw some pictures as examples. So I think the first way that we could say that it fails is that f is not continuous at c. So if I have a picture that looks like this, if I have a set of axes over here, and this is my c, and then, you know what, maybe my function looks like this, and then it jumps, and then it looks like that. F does not have a derivative at this point. In fact, it's not even continuous, right? What's the second situation? The second situation is maybe you have a cusp or a corner. So in that particular situation, your curve might look like really like what we looked at up above in our earlier example, but maybe the curve looks like that. So in this particular case, it has a cusp right here at this point. That's a cusp. Another example would be absolute value. If you looked at absolute value, the graph of absolute value looks kind of like this. That's a straight line. This has a corner right here at 0. Okay. And the third situation where function will fail to be differentiable is when you have a vertical tangent line. All right, so I guess I've been drawing axes, so I should draw another axis here. My curve will still be in blue. So if you have one of these like S curves where somewhere in the middle it's vertical momentarily, then in this particular situation, when you have that vertical tangent line right there, that's going to be a case where the function is not differentiable. So this usually manifests when this occurs when our derivative has a 0 in the denominator and usually something non-zero in the numerator. All right, so those are the 3 situations where our function will fail to be differentiable. We'll look at more examples in class together. All right, everyone, take care.